let me begin. And this is based on the paper we did here last year, November last year, and also course in progress, which is basically supposed to appear later this year. So let me begin with a motivation. So we have here conformal blocks, and conformal blocks are known to be sections of bundles. So certain bundles over the configuration space. And this is definitely true for these, or everyone is familiar with this story for the rational CFDs. And there are some analogous statements for the other cases. And so this is usually conformal, this refers to conformal blocks with insertions of primaries, which are highest weight representations of the Virasoro algebra. And now there is a certain question, namely what happens if we have insertions of other Virasoro modules, so-called irregular modules. So this is the main question I want to tackle. So the main question is what happens for irregular operators. So what do I mean by this? So let's consider a conformal block with some operator insertions, and this is basically their conformal weights, and you have n of them, and eventually you have another operator, some irregular operator. So this one here is some irregular operator, and it's say inserted at infinity, and these are conformal primaries with conformal weight given. Okay. So this is the main question which I want to address, and in this talk I will focus or restrict myself actually to the insertion of certain degenerate operators in Liouville theory. But before coming to that, let me first remark what this is useful for. So this is useful for two things which come to my mind, namely the AGT correspondence. So we have 40 Staglas theories, and these basically can be described in terms of Liouville theory with irregular operators, right? So that's definitely one application, and there was already a talk about this, and that's definitely maybe at this point the most important for this workshop. But there is another one which comes to mind, namely one could ask about generalizations of the braiding properties and S&T transformation properties of these kinds of blocks. And this, when you have such an irregular state, and that will lead to a generalization of the notion of MTCs, or modular tensor categories. So, and this is relevant for topological phases of matter. So basically, the question here would be, what are generalizations of MTCs presence of so-called irregular defects. So that would be connected to, again, questions of monodromy. So for these kinds of conformal. So this is maybe the motivation. Let me now come to another point, namely why called irregular. So these are certainly these operators, as I will discuss in a moment. They are not in the usual representations of the Virasoro algebra. So they are in different modules, and you can call them however you want. But they are called irregular because they're related to these conformal blocks are related to irregular singularities, and that has to do with these connections on these bundles. And if you consider conformal blocks phi, which is basically a block of some operator as z0 and another operator as z, and so on and so forth. If you view this as a conformal block and view this as a section of a bundle, this would be locally some vector, and then you can have two cases, namely you can have d phi dz in the vicinity, so near z going to z0, you can have something like a0 divided by z minus z0 times phi. So this is in the vicinity of this point z0, this would be regular. And that means that these operators of z0 would be regular. And you can have this behavior where you actually have something of a higher pole. So this r here is greater than 1. And that's the case which is irregular. And this behavior will indeed show up. So you see this is kind of an ordinary differential equation describing this connection and the irregular singularity at this point, and that's the typical behavior we will be seeing. So there is also, of course, corresponding higher order ODE, and this one is just P and F and P1 so on and so forth. And so this is irregular if and only if basically z minus z0 to the n times pn of z is not analytic at z0. So these are the descriptions. So this is basically first order, and this is in terms of, let's say, one of the components will satisfy this higher order equation. And this is how you characterize these irregular singularities from the point of view of these differential equations. So let me also briefly say something about the conventions I'm going to use. So okay, so we will consider 2D Liouville theory. With the following definitions, you have Q is B plus 1 over B. The center charge I denote by C hat because I'm going to use C for another purpose later on. q square, and we have the conformal weights, which is alpha times q minus alpha, and this alpha is called the Liouville momentum, and here b and alpha are both, can be both in C, generically. And you have, and what is also important for us are, the generate operators. So first of all, these guys here correspond to vertex operators, the usual vertex operators. They are just labeled by these Liouville momenta, and it is e to the 2 alpha chi z, where this is this Liouville field. And we have also the generate operators, which will be of interest, and those are labeled by R and S. This exponential of r minus 1 plus minus 1 times chi. So this will be the generate operators. Okay. So these are the conventions which I'm going to use. And now let me, are there any questions about the motivation maybe, or the background? Otherwise I will go straight to the irregular representations. I guess the audience is very familiar with this stuff.
Is sign this one, not 1 minus r?
Let me see. Ah, right. 1 minus r.
1 minus s.
1 minus s, yeah. Like this.
Mm-hmm.
Good. Yeah. Okay. So
sorry, what is n t?
Oh no, this is just these are just positive integers. Okay. Good. So, other questions? Okay. Now let me go to the irregular representations. Of Soro algebra. Okay, so let me start with the definition. So if we look at a rank R irregular states, and they are defined as follows. For you will have something like Lm acting on this irregular state is 0 for m greater than 2r, and you will have L 2r acting on it, giving lambda r I. So this is already the novelty here, that these guys, which should usually annihilate the state, the highest state representation. So these are not high state representations, they're eigenstates of these positive elements. And this will just continue. So, and you will have a non-trivial action all the way until L0. And I will gonna specify this, let's say for the simplest case, which is rank 1. So the simplest rank 1 case, these become as follows. So you will have L2 acting on the state, which will be labeled by some parameter C and another parameter alpha. Alpha is again the Liouville momentum, but C is some arbitrary parameter. And this is C squared over 4 times C alpha. So this is the eigenvalue here. This is what was denoted by lambda r or lambda 2 here. Then we have L1. That is just minus C times alpha minus Q. And we have L0. And that is given by delta alpha plus C del C acting on this. In particular, L0 is actually acting non-diagonally because there are derivatives with respect to this parameter here, so it's not a usual eigenstate. Right. So that's in the simplest case of rank 1. And again, as said, alpha here is just Liouville momentum, and C is some constant, some parameter, if you want. The way to think about it is for these rank 2 guys, they can be engineered by letting 2 primaries collide, and so they will have, each of them has a Liouville momentum, alpha 1 and alpha 2 and so on, so there are kind of 2 parameters attached to them, but they collide in a kind of non-trivial double scaling limit, and which will form the state. So there will be only one parameter left, so you send actually alpha 1 and alpha 2 to infinity while keeping the sum constant. And C roughly captures the remnants, because originally you had of course these 2 guys, but then these moduli are hidden in these 2 parameters this way. So the moduli space is not reduced, but it is kind of just packaged differently. And okay, so this is so far what this was of course invented first by Gaiotto, and then people in the audience have done important work on this, and Gaiotto and Teschner have also further developed this formalism here. So this is all nothing new, just a recap of what is known. But what we can now also say, and I'm going to generalize this to a higher rank in a moment, is that we can also write the corresponding vertex operator for these states, so using the operator states correspondence. So corresponding vertex operator here would be this guy. So we have 2 alpha chi times the exponential of 2 C del chi. And actually here I want to insert the operator at infinity. So with L going to infinity. So this would be the corresponding vertex operator, which will be also important when we compute conformal blocks. And the analogous operator for the higher rank irregular states is similar. So more generally, we have the following, but before I proceed to that, any questions about the definitions here? Maybe this is new to some people. Okay, good. Let me proceed. So more generally, we have that the rank n irregular vertex operators are given as follows. So I will denote them as follows. So they will depend on some alpha and a collection of parameters C. As you see, they will depend, as was mentioned in Oleg's talk also previously, that they depend actually on R parameters. Lambda here, you can re-express these lambdas in terms of parameter C, so they will depend on n parameter C and this alpha, and the corresponding vertex operator has the following expression. So you have exponential of 2 over n factorial Cn del n chi, and you have exponential of 2 over n minus 1 factorial Cn minus 1 del n minus 1 chi L, and so on and so forth until you get to 2C1 del L x 2 alpha chi. Again for L going to infinity, because we want to insert this irregular state or operator at infinity. So you see that higher order derivatives of this field appear here in the exponent. So this is known, of course, to be corresponding to these primaries, or if alpha is chosen accordingly even to the generate fields. But these guys, there will be not eigenstates of L0. So there will be, the action here will be more complicated, and you can actually check this ansatz by computing the OPE of the energy momentum tensor of these operators, and check that you indeed get the correct, for example, for rank 1 you get these guys, and for higher rank you get the corresponding generalizations with several parameters C and so on and so forth. So you basically check this by computing the OPE with the energy momentum tensor.
So the last derivative is with respect to alpha?
No, there's no, that's just a 2.
This is
just
2.
a convention,
This is
2
from
alpha,
here. Okay.
to get all the constants right, and
Okay.
It will basically reproduce these equations which are written in your papers or Gayota Techner's papers. Yeah.
Yes.
Okay, so what are these vertex operators now useful for? The goal will be, as I said, to compute conformal blocks. And for the generate fields, we know that we can use the Coulomb gas formalism to compute such conformal blocks. And that's what I'm going to stick with. I'm just going to use also these vertex operators, and then use the Coulomb gas formalism to evaluate these, get the expression for these conformal blocks. So that will be the strategy. So that will bring me to part 2. Okay. So if there are no questions, I will just erase this. Yeah, the expressions of these lambdas and how they act, you can look them up in the papers. If you want, I can also write them down, but I think it's not so relevant at the moment for what is going to come next. Okay, so I'll just...
So your n is
the rank
integer or
integer. In my case, it's integer. Yeah.
And you cannot move to half integer.
We have not tried that. We were doing this stuff for now, because I'm going to derive connections for these, and half integer maybe it's also possible. Yeah, we just didn't look at it. Okay, so let me come to integral representation of these conformal blocks. And in order to do that, we have to introduce screening charges at positions Wi on P1, and the corresponding conformal blocks of one irregular operator and an arbitrary number degenerate operators can be expressed as follows. So here I'm using the generate operators. So this is a bit different from the construction of the relevant, say, 4D dual theories or Argyll-Douglas theories, because there you have sometimes an irregular state or even two, and some other operator, but it is not the generate. But you can also have theories where there is just one irregular state, and for those this would apply. We can also generalize it, by the way, to two irregular operators inserted at different points, but I won't talk about this in this talk. But if you even consider one irregular state and arbitrary degenerate operators, this will correspond to certain 4D theories with the insertion of surface defects. So that's where this will be connected to. But let me now write down these expressions. Okay, so I'm going to focus on rank 1 first, and then we will gain higher rank. So for rank 1, you will have, this is the expression of the conformal block, and it is given in terms of an integral over a certain cycle. The cycle will be a non-compact cycle, and I will come to that in a moment. And then you have this mu, which I will explain also, and you have the screening charges. So you have a product over screening charges at positions WI, and then you have products over some degenerate fields, minus Ka over 2b at ZA, and you have some irregular operator labeled by alpha and C, and you have to integrate in these W planes. And this guy here, this is a non-compact cycle, so-called Lefschetz cycle, or thimble, if you want. It has to be non-compact because, it's defined in a particular way, which I can explain actually. So if you view this, so this guy here, this is actually the Wick contraction. This operation here is new, and this is usually rewritten as some exponent of some W, which is known as superpotential over B squared. So this would lead to some, if you want, for small b to some WKB approximation and so on, but we don't have to do that. And the contour here, this Lefschetz thimble, has the following properties. So if you are on this W plane, say you have just one screening charge, then it will typically, well, there is no color, okay, nothing. It will typically look like this. So this would be this gamma, and it has the property that at the boundaries, this W over B squared goes to minus infinity. So this will make sure that this integral is convergent, and you can compute these contours by gradient descent or Morse flow if you want. So there are various techniques to actually specify them and so on. But yeah, these are the integrals which we are going to be interested in. Let me also write down what this Wick contraction eventually gives you. This guy here, basically, yeah, actually compute it. It is given by, yeah, proportional, if you want, to product over I equal to J, Wi minus Wj times minus 2 over A squared. And product over I and A, Wi minus Za to the power of Ka over B squared. squared, and you have product over A B, ZA minus ZB to the power of KA KB over 2 B squared times, so this is the weak contraction of these degenerate operators with each other, but then you will also have to contract with this irregular one, and that will create an exponential, which is roughly as follows. So you have the exponential of lambda times sum over I minus 1/2 sum over A KA ZA. So this is what you will eventually get. So you will first do it, use the operator expression with this L, and then you do all the weak contraction, then send L to infinity. And this lambda here comes up because we set basically C to be lambda over B to get here this B squared. And right, so this is kind of work.
This is for rank 1.
So this is lambda over B squared.
Yeah,
Yes.
Is this for rank 1?
This is rank 1, but we have the expression for higher rank. I'm going to write down in a moment. Right. So this is rank 1, and let me also do actually higher rank. So, but
this you have yet to integrate, right?
this we have to yet integrate.
And so what you can say?
But I'm going to actually, so there are various techniques to integrate, but I'm going to actually derive differential equations satisfied by these. And then you can solve those. And there will be asymptotic solutions because it's irregular and so on, but that will be the strategy.
And why you take only one set of screens?
Have several screening operators.
Yeah, but all with 1 over B.
Yeah, well, we just looked at this simplest case so far, so it's just work in development. And I'm also going to focus, in the following. We focus on insertion of only one screening charge, so not to clutter the notation, because for the higher rank it will become more complicated. So then the Lifshitz symbol, it will be really like this. It will be for one screening charge, which is 1 over B, it will be really of this form. And now I can also do this case of higher rank. Let me do it here. Yeah, so we have basically one screening charge with 1 over B, and for certain applications which we were looking at, because we started with conformal blocks of purely degenerate fields, and then the particular fields we are interested in, there was enough for if you have no irregular operator, it was enough to consider this one. So you could get for the subset we were interested in, you could actually use these to get all the conformal blocks. So that was maybe one motivation. But are there any other questions about this story here?
So these,
Yeah.
I guess all these W will have some branch points, right? Because
Sure. Yeah.
So
There will
this
be
contour
branch
actually-
points and all kinds of. This, you mean this W here?
Yes.
Yes.
So the contour in some sort of covering space.
Right. This is in a covering space. Yes. Absolutely. Yeah. You can focus on let's say looking at deriving monodromies using Stokes phenomena only from this expression. But this is not what this is something we also did, but I'm not going to go along that line. I'll just focus on the differential equations, which we're gonna derive. So,
you said that the integral should be convergent, right?
yes, it is.
But if you have just a single exponent of W and with such contour, on one side it goes to 0, at another to infinity.
No. You extend it on the other side as well. You do on both sides, so it goes to on both sides to minus infinity. This W. You can do that. then it will be convergent. It's not compact. On both sides it goes to minus infinity, here and here.
What?
You can start with a critical point and then flow, but then there is another flow, actually, starting from there to the critical point, and that will give you also minus infinity. So this is how you can construct these cycles. So that can be done, actually. One example is, for example, where it was not done in this way. For the simplest case, just Bessel functions. They have these kinds of modified Bessel functions, but they have these kinds of integration functions, right? And it fits exactly with this. So that's fine. But let me actually proceed. So if we do rank n greater than 1, then the whole thing looks as follows. So you have this this integrand, which is 1 over b w, because I have now just one screening charge, and A, and I have the irregular higher order operator here at infinity. Then this one will actually give you the following expression. So you will have some delta function alpha plus 1 over b minus sum over a ka over 2b minus q. So this is just some charge conservation story. And then you have a product w minus za ka over b squared. This is still all the same. So you have minus ka b over 2b squared. And you have then also exponential of n minus 2 ci I 1 over b w to the power I minus sum over j minus j z to the power zj to the power I over 2b. And we're going to rewrite this as q times exponential of w over b squared, where now this w here.
Sorry, can I?
Was the question? Yes?
Yes, I didn't want you to erase that formula.
Which for? So.
No, I was asking, so this integral representation,
Yeah.
can I think of it as like some matrix model type of representation, right?
Right.
And this would be like a Penner type of matrix model.
Right.
And there were some people some time ago who studied Penner type of matrix model.
Yeah, they did actually. I found it also in the literature. But what they do is they don't have these z's. They just integrate over these w's, and they get you some number.
Yes, but if you insert, but this is because they don't have the degenerate field insertion. But
Right.
typically when you have the degenerate field insertion.
They do it for Landau-Ginzburg.
Yeah, but when you have the degenerate field insertion, usually what you do is that you take the same matrix model and you add some determinant type.
I
insertion.
see.
Is this what you are doing here?
That's probably, yeah, you have to show me that literature, but maybe it would be equivalent. I don't know in which context this is.
Yeah, it's precisely in this context of irregular.
Okay.
Is
Okay, then we
one of the authors is Rim and the other is they are.
Okay, we can
Yeah.
talk about it. So, yeah, so this W here is basically dependent on this W and a collection of these Z's, and you get sum over A, Ka of log W minus ZA minus A less than B of 1/2 Ka Kb log ZA minus ZB minus 1 to n 2 Ci over I Wi minus 1 over I Kj Zj to I over 2. Okay, so maybe there is one remark at order here. So this would be the superpotential. It's logarithmic up to these polynomial terms in this W, and it's a polynomial of order n for a rank n irregular operator. And one remark here is that if you, for example, evaluate this kind of expression, because this is 0, then you can, so this is basically dw e to the w over b squared. This is basically equivalent to L1 acting on this conformal block F gamma. That means that you have sum over A, del A, so del ZA of this F gamma, and you have minus all these operators and L1 acting on this irregular state. So this is basically telling you that this conformal, global conformal condition given by L1 is satisfied. This is automatically built into this. And the others are kind of related, and I will come to that. So let me, any questions so far about?
So your delta function means that you actually have here a theory of free field with conservation.
Right. Because
Not Liouville.
this is Liouville. Yeah.
No, in Liouville there is no such conservation.
Well, but I have the charge, I have the screening charges,
Yeah.
right? And those have to satisfy charge conservation.
In free field theory, but not in Liouville.
But if you have these irregular ones, you can, this is one way to evaluate it, right?
No, it's just the context in which you make it.
Yeah, this is a free field computation, right?
But in Liouville, there are residues of correlator which are expressed by such integrals.
I mean Liouville.
In Liouville as well, right?
Hmm?
If you have degenerate
what
field-
we say just that in Liouville you have the integral and
Sure.
over zero mod which gives you poles
Right.
with residues.
Which are like
here,
this,
like
right? That's what I'm doing. So let me actually come. Maybe I should leave this because, well, there might be some questions. So I will just put it here. Okay. So what do I want to actually do? I want to compute flat connections. Right? So we have the case of rank 1. I'm going to focus, probably there will be no time to go beyond that, but that's already interesting. So we're going to define a function phi gamma of z to be basically integral over gamma dw product over I w minus zi to the ki over b squared and e to the lambda over b squared w, right? And this whole thing I'm gonna denote as the exponential of some w tilde because I have stripped off the purely z-dependent part from this conformal block. So I have product over I e to the minus lambda over 2 b squared ci, and then you have I equal to j ci minus zj minus ki kj over 2b squared phi gamma z. So this is the only non-trivial part, which is w dependent, and this is only z dependent. And I'm going to focus on this function, and then there is the following theorem. Okay, so now define a wave function psi, or a vector psi, which is del phi del z1 all the way to del phi del zn, right? And then we have the following statements. Psi satisfies the differential equation del zi psi is equal to ai psi plus sum over j not I omega ij over zi minus zj psi, where this a is, let's say, given by the following thing. So this is lambda over b squared. Everything else is 0. And so this is in the ith row and column, this entry, and this omega ij is roughly given as follows. So, k here, 1 over, let's say, p squared. Then we have ki minus ki minus kj. Ah. And so this is basically ji. All right. And yeah, so the second point here would be that this connection defined this way is flat. So this is a kind of KZ connection, but this A here does something non-trivial, AIs, right? They will basically, yeah, this creates an irregular singularity at infinity of rank 1, indeed. So this is what it is, and so this is actually something we can prove by
If you say KZ, what is your current algebra?
Exactly. So it looks like KZ, but we didn't start with any current algebra or anything like that. So but it comes out. But we are actually now looking at irregular representations of yeah, some GLN modules and so on. And this kind of structure, it might be related to that. That might be hidden there. So these blocks here, these irregular
But
states.
the rank is related to the number of points, right?
It's just, so this is very different from the usual KZ. The rank is linearly dependent from the number of it. It's not an exponentially or anything like that. It's just n. It's just the number of points. So this is indeed, yeah, it might be related to GL1, irregular representations of GL1. So this is what it, yeah. But we can actually, yeah, we can have some more comments. We can actually prove this. So now the proof is basically the first step for the first part is you basically differentiate. You have these integral expressions, right? You differentiate under the integral. So differential. I just give you the strategy. Differentiate under integral and use that integrand. And use maybe use partial integration. And that integrand basically vanishes at infinity at boundaries of gamma. And the second part is that we just show the following. We just use the following, so which you can easily convince yourself because the matrices are explicitly given. Omega ij plus omega jk, comma omega ik, commutator is 0 when I, j, k distinct, and moreover omega ij, comma omega kl is also 0 when I, j, kl distinct. So this is basically some results, and if you know this, you can just put it, plug it into the usual proof of the KZ equation, and then the connection is flat. So that just shows it. And so this is basically what I want to say about the proof. But now, in the remaining time, let me connect back to the conformal blocks, because these guys were not really the conformal blocks. This was some piece of the conformal block, right? And then you take these derivatives. But given these equations, you can actually, as a corollary, show that it indeed the corresponding function f here defined in this way, with this integral, satisfies the modified BPZ equation, which is important because only that tells you that it is actually the conformal block, right? It has to satisfy the modified BPZ equation for this particular case, because this is just some, I'm going to insert some degenerate field to 1, 2, and then it will be second order. So let me also show that. Any questions before I erase this stuff about the connection?
Maybe about the notation. So if it were not irregular conformal plot, but just regular one, so what would be the momenta?
The momenta are, well, the momenta are these degenerate fields labeled by the Ka. The Ka, right? Ka over B. Minus K. So the momenta are actually minus Ka over 2B. Right? Ka are some integers.
Do you mean moment in the intermediate channel or what?
No.
The Liouville
All of them. Already, how many primaries do you have?
This is for arbitrary number of primaries. Let's say you have some capital N primaries with the Liouville momenta Ka over 2b, where Ka is some integers. That's basically. And yeah. So that's with that. And these Kas are the same which appear here. So they are labeled by Ki, Kj here. They are labeled here. And they appear in this connection. Right? So, so let me now actually come to this corollary of it. And maybe I'll just erase this part. And easier. So, there is a corollary here that this f gamma z, which is which I take to be the corresponding integral representation. I'm just using this now as a definition. Some k0 over 2b at 0, and then you have 1 over 2b at z. So this would be this field 1, 2, and then minus k1 over 2b at 1, and I have infinity. So what I mean here is the integral representations defined previously, right? So if I have such a function, then this function satisfies the modified BPZ equation. So which one is this? This is just
When you say integral representation, the number of screenings comes out of this.
of the charge conservation, right? I will focus on the simplest case where there is just one green charge. And then you have these curves. So this can be actually always arranged by choosing this alpha accordingly. And we have this b squared del b squared minus 1 over c minus 1 del c. So this equation can be derived algebraically using L0, L1 invariance, and action also of L2. Then you get this equation, right? Using the irregular modules, not the usual ones. So that's why it will be a little bit different from the usual BPZ equation. And as you said, where the alpha here is just b plus 1 plus k0 plus k1 over 2b. And this was just this charge conservation. Actually, what is interesting is that this alpha itself never shows up in these integral representations, right? right? And even if you do the Dweck contraction, you have this exponential and so on, but there is no alpha there. But it kind of miraculously comes out, if you view this equation, it is only satisfied for this alpha, which is the correct one. So it's kind of hidden there, which it should, because it's just, you know, it has obeys some constraint.
What happens if you adjust alpha in such a way that you need no screeners? What happens to this block?
That, we always had a screening, at least.
No, but you say that it depends on alpha, yeah?
Right.
The number of screens can be adjusted by choosing alpha.
Right.
Let's do, and you chosen to have one.
Yes.
Let's simplify it.
Right.
Let's choose it to have 0 screens.
Okay.
What happens?
I haven't looked at it. Should look. Maybe we can talk about this afterwards. Yeah.
It's not obvious.
It's not obvious to me either. Yeah.
What happens?
What happens? Is that just a reconstruction result and without any integral? Or?
Yeah. Well, according to what you say, there should be no integral, but they should be still, since you have the general field, they should be the equation.
Right. But this one definitely satisfies PPZ. The other one, I don't know. Maybe it doesn't satisfy, but one could check this. Maybe it will. So that would be interesting. So yeah, that's actually it. And I won't have time to go to the irregular. But there will be a similar formula actually for the irregular, higher rank irregular cases. This A and omegas will be a bit more complicated, but they will still satisfy the flatness condition. So that you can show, but yeah, let's leave it at that. Okay,
Questions?
Yeah.
Questions about this choice of gamma. So polarizations one usually has to pick some critical point.
Right. Yeah, so that actually fits nicely because you see this is an n vector, so it will have n solutions, right? And so it should be basically consistent with the choice of, there should be exactly n cycles gamma. And indeed, this W has exactly n critical points, and from each of those you can create this Lefschetz by flow. So that fits indeed.
And you mentioned you can crystal study Stokes phenomenon, but does it play some role?
So yeah, you can study Stokes phenomena directly with the integral expressions, which we had, or from the differential equation point of view. And we did study it from the integral point of view. Yeah.
What are the Stokes sectors, and can you describe?
Well, in this case, from the point of view of the differential equation, there is only one irregular singularity at infinity, and it is kind of rank 1 or 2, whatever convention you use. So there will be 2 Stokes lines. So, so there are 2 Stokes sectors.
Two Stokes lines, what are the Stokes lines?
That we didn't compute for this case, but we can do it. But we did it from the integral representation point of view, and it's, yeah, it will give you some. You know, actually, you can construct grading matrices from these things, and they will satisfy Yang-Baxter equations and so on. So this all fits in that sense. So they are valid representations of the braid group, whatever you get. Yeah. You can express it in terms of Q, which is e to the 2 pi I over b squared, and then they will depend on this b. So there will be, you know, like usual, like in Schoen-Simons theory, it depends. You get something depending on Q. It's similar here.
I wanted to ask, is it true that this flat connection does not depend on the number of screenings in the integral?
Right. Yeah, and this is derived for one screening charge. We hope that we can actually extend it to arbitrary.
Okay.